Okay, in this video, we want to derive a formula for determining the volume of surfaces of revolution. And to get us started, consider this curve here. It goes from x equals a to x equals b. Suppose we took this curve then and we rotated it about the x-axis so that we generated a solid three-dimensional figure that might look something like this. And we want to find the volume of this three-dimensional figure. And to go about that, let's look at the problem like this. Here is our curve that goes from A to B, and let's say that we're along the x-axis here. We're going to consider this a part of it here, delta x. So it goes from here up to where the curve is. And suppose then we took this strip right here and we rotated that about the x-axis to give us a strip of volume, delta V. Is there some way that we could at least approximate what this volume element would be, what this strip of volume would be? So let's take a look at this diagram. Suppose that, again, we have delta x here. We take it up, and then we form this rectangle instead. Now when we do that, we're cutting off out of our curve here. So let's keep that in mind. But if we form this rectangle then, and we rotate that about the x-axis, that's going to form a solid circular disk. And the volume of that solid circular disk, that would be approximately equal to this strip of volume here that we just created over here with this figure. So let's take a look at the circular disk that we formed. That would look something like this. Its width is delta x. The rectangle had a height of y, so the radius of the solid circular disk will be y, and the volume of it, I call it a solid circular disk, really it's a cylinder. The width of it is delta x, and the radius of it is y. The volume of the solid circular disk, or of the cylinder, that would be equal to the area of the circular face multiplied by the width, delta x. And the area of that circular face is pi r squared, but here y is equal to r. So our volume for that solid circular disk that we formed here, that's equal to pi times y squared times delta x. So the volume of the strip that we formed here, that's approximately equal to pi times y squared times delta x. Now here we did that just for one section here along the line segment AB. Imagine if we did it along the total segment from x equals A to x equals B. We split it up into these rectangles. We rotated the rectangles around the x-axis to form a solid circular disk, and then we added up the volume of all those solid circular disks from x equals A to x equals B. That would give us the approximate volume of our two-dimensional figure here. And then if we refined our process, we kept making delta x smaller and smaller until finally it approaches 0, so that now we have, instead of delta x, we have the differential x. Then we can say the volume is exactly equal to the integral of pi times y squared dx, taking our limits from x equals a to x equals b. And so that is kind of like a common sense approach. It's not a proof by any means, but hopefully it makes sense to you as to how this volume integral is obtained. And come back then, join us for some of the other videos, and we'll use this volume integral here to solve some problems. And also, we'll consider how we can derive this when we have to deal with parametric equations. So come back and join us for those videos, and we'll see if we can start solving some problems.